All right, hi. So my name's Mark, and today I'm going to be talking to you about some recent KHI results that we've got here at UWA. So firstly, a bit about me and I guess what I do. So in terms of my uni background, I did a BSc at UWA in 2018 in chemical engineering, and I'm currently a final year student in the Masters of Professional Engineering. I started as a research assistant last year, and I'm finally, after a long wait, commencing my PhD next year. Outside of uni, I play both hockey and cricket. So that's a photo of me and my mate in the top right managing to win the flag last year, which was pretty good. I'm unfortunately quite a passionate Carlton supporter. So if there's any Eagles fans in the audience, please leave me alone. And I'm also training for the Rottnest Channel Swim Solo next year. So hopefully in terms of what I'm going to talk to you about today and what I'm going to show you is that we need both induction time and initial growth rate measurements if we want to accurately screen KHIs for a given application. The apparatus that we have here at UWA, which is called HPS-ALTA, can provide these in a time-efficient manner. And this is a really big barrier to other apparatuses that are used in this field. The KHI rankings that we get out of this system can change with subcooling, and also the gamma distributions can accurately describe KHI formation probability. So firstly, I guess a kind of a bit of a refresher on what KHIs are. Well, they're a hydrate management technology. So they're polymer-based compounds which can delay the onset of hydrate formation and/or growth. And obviously, if we can push hydrate formation delay periods to longer times or make the problem less severe, we're reducing this blockage risk. I've got some examples of some common KHIs on the bottom side of this slide here. So they're mainly both centered around this PVP PV cap polymer, and you'll see that this is present in quite a few of the different KHI chemistries. The most important thing, I guess, in terms of an economic perspective for these inhibitors is that they require significantly lower dosages. So we're on the order of 0.1 to 1 weight% as compared to tens of weight% with thermodynamic inhibitors, and this has a potential CapEx and OpEx reduction. So firstly, one of the ways we can look at KHI performance is via their effects on hydrate growth rate. So what we're looking at on this plot, on this figure here, is the gas consumption rate as a function of subcooling. We use the gas consumption rate as a proxy for the hydrate growth rate, because when hydrate forms, gas goes into that phase, and so we see a pressure drop. And what we're seeing here is results for both KHI-free and KHI-dosed systems. And the main thing we can take away from this is that we see, despite the higher subcoolings present in those KHI-dosed systems, we're seeing growth rates that are orders of magnitude lower. And comparing KHIs by this method, so their effect on the growth rate and how well they are able to reduce the growth rate, forms the basis of what we call the crystal growth inhibition method, or the CGI method for short. And under that method, we would say that the better KHI is the one that's more effective at reducing the growth rate. So it would have a lower value on this vertical axis. Aside from growth rate, we can also look at hydrate formation. So hydrate nucleation itself is a stochastic or random process. And what this means is that when we enter the equilibrium region, we've got a certain formation probability associated rather than a deterministic problem. And this gives us two types of experiment that we can look at. So we can either look at a constant cooling experiment. So this is when we cool the system into the equilibrium region at a constant rate, and then we measure a formation temperature. From that formation temperature, we can then calculate the subcooling. The other way we could do it is with a constant temperature experiment, where we crash cool the system into the equilibrium region and then hold at that temperature for a period of time and measure how long that period of time takes before we form hydrate. Typically, what we see is that KHI-dosed systems yield longer induction times, so that's at a constant temperature, or higher subcoolings. And we've got some results here on the right-hand side of the slide. We're looking at how either the subcooling or time changes or varies, I guess, with the formation probability. So the most important takeaway here is that either induction times or subcoolings are a distributed property of the system. So it's really important to get lots of measurements. And I'm actually going to show you an example of why it's important that we take these large data sets and get lots of measurements. So this is a real data set that we've measured here at UWA. And we're looking at how the cumulative mean induction time on this axis, so that's the cumulative mean of the wait time for hydrate formation, changes as a function of how many events we measure. So just by chance, our first induction time is up here at about 40,000 seconds. I should have also mentioned this is a KHI dose system. But then when we begin to measure more and more events, our cumulative mean actually drops. And it ends up at around 1.4 times lower than that first measurement. And what this is really showing us is that we need big data sets, especially bigger than, say, 30 or 40 formation events, pushing towards 80 or 100 events, before we start getting a really good idea of what this mean induction time is. And aside from just an induction time or a subcooling experiment, this is actually telling us something about the formation probability itself, which is that small data sets can't accurately capture formation probability. And this has a large implication for picking your best KHI for a field, because if you can't accurately capture the formation probability, then you can't accurately depict how a KHI is performing. And if you can't do that, then you have no way of ranking KHIs for a given application. So even something that might seem as, I guess, inconsequential or a little bit trivial in terms of a fluctuation in the induction time can actually have a big impact in terms of what the outcome of your experiment is. The apparatus we use here at UWA, which Bruce introduced earlier, is called the HPS-ALTA. And that allows us to collect high fidelity data sets in a time efficient manner. And that's both formation events and initial growth rate events. So those formation events are either subcooling or induction time events. The most important thing with this system, I guess, is that it's a stirred system and it has a small thermal mass. So what that lets us do is cycle in and out of the hydrate formation region rapidly. And so we can get lots of events in a very time efficient manner. So our apparatus can go through these events on the order of a cooling rate of approximately a Kelvin per minute, where traditional apparatuses can cool in the order of, say, a Kelvin per hour. So that's what this last point here is getting at, is that time efficiency, when you have to, say, measure over 30, 40 events, is a major barrier with alternative apparatuses. We've also got multiples of this cell, so we've got 16 or even more of these ones currently, and we've got some other ones that we're developing of different sizes. So moving on to the results, I guess, of the performance tests we've done so far. The first thing we can look at is what different chemistries are there out there. And we first looked here at Innovex 501 and Innovex 713, and we've dosed them both at 1 weight percent individually. So we're looking at either the impact of Innovex 501 or Innovex 713. In total, we measured over 1,200 hydrate formation and initial growth rate measurements, and here we're looking at induction time results. So the reason why we picked these two chemicals is that Innovex 501 has the same copolymer structure as Luvicat 55W, which was another KHI we'd looked at previously. And that lets us look at the effect of the solvent package, because both of these chemicals are dissolved in slightly different solvents. And Innovex 713 also has the same PVP-PV cap structure as Innovex 501, but it also has this additional side chain. So now we can start to look at the effects of this side chain, and what the effects of different copolymers. So firstly, having a look at our results in terms of the KHI effect on growth rate. Well, as before, the first thing we can see is that our KHI dose points are much lower than our KHI-free points, despite the subcoolings being much higher. And as before, a lower value on this axis means that it's a better growth inhibitor. We can also see that Innovex 713, which is these green circles, is about an order of magnitude higher than Innovex 501 over this full subcooling range. So what this might potentially be telling us if we looked at the growth rates is that Innovex 501, so these green triangles, is an order of magnitude better inhibitor for all applications. So that's in terms of, I guess, the relative difference between the two KHIs. This result tells us that Innovex 501 is a much better inhibitor. The other important thing to take away from this is it's a much better inhibitor over all the conditions we've measured. What's really interesting, though, is if we start to now look at the effect of the KHI on the induction time, so not the growth rate, we don't see the same trend. So at this, with this plot here, looking at the mean induction time as a function of subcooling, and of course, a higher value on this vertical axis is better because it means we're able to delay hydrate formation for longer periods. And what we see here at this low subcooling is that Innovex 713 is actually able to delay hydrate formation for a longer period. That's not what we saw with the growth rate results, which showed us at that low subcooling that Innovex 501 was still performing perhaps an order of magnitude better. And what this is essentially telling us is that the growth rate alone, or just looking at one aspect of the KHI's performance, doesn't really give you the whole picture, and it also overstates the relative differences. So concluding, for example, from this plot, that Innovex 501 is an order of magnitude better than 713 isn't necessarily true when you start looking at other aspects of how the KHI is affecting formation. So aside from looking at, say, the mean induction time, we can also look at how all of the distribution of induction times changes with and without the presence of KHIs and what implications this has. So in a KHI-free system, on the left-hand side here, we're looking at how the cumulative formation probability on this axis changes as a function of time. And the key point here is that these solid line fits to the exponential distribution, which we've shown can capture formation probability in KHI-free systems. And the key point of this exponential distribution is that there's appreciable formation probability at short induction times. And what that means practically, I guess, is that these distributions are quite wide. So at values below, say, the mean here, we have this region of appreciable formation probability. When we add KHI into the system, though, aside from seeing delay in terms of the hydrate formation onset, we're looking at 3 times greater subcoolings here, yet our induction times are on, say, the same orders of magnitude as our KHI-free system. We also see that the fundamental shape of the distribution has changed. And most importantly, they're much steeper distributions. So now, as opposed to these KHI-free systems, where we have these times below the mean with appreciable formation probability, we have a much narrower distribution in here, and it's much steeper, which means that that spread is reduced quite a lot. Moving on to some implications that this potentially has for an industrial production system. Well, the first question is if we have, say, these big induction time data sets with lots of events, and we can see how they vary with probability, well, the question is, we've got all these probabilities in induction times, how do we pick the most meaningful one, or which one's best for a field application? The problem with using the mean induction time, which I was talking to you about before, is that it implies that we can accept a 50% formation risk in our system, and that's obviously not true. Every time we are producing, a control volume of fluid, we don't want there to be a 50% chance the hydrate will form. So in fact, for an industrial system, the more relevant points are actually these low formation probabilities in this sort of region here. And that comes back intrinsically to the shape of the distribution, because that changes how these low formation probabilities are associated with time. So one way, and a recent way we've been working on doing this, is by using the gamma distribution to capture this relationship between induction time and probability. So that's these solid line fits to the induction time data sets. And an advantage of using the gamma distribution is that it's both continuous and smooth. So this lets us estimate the induction time for any formation probability. So an example of how we can do that is, let's say, for example, we could accept a 20% formation probability. And let's call that our threshold probability, TPR. What we then do is take our TPR and use the gamma distribution to estimate the time corresponding to TPR at each subcooling. So that's pretty much, as I've shown here, we just go across and find the intersection with the curves, not with the experimental data sets, and read off the time associated there. And we call this time TIPT. We can then look at TIPT for different inhibitors, because this lets us adjust the value of the threshold probability and see that relationship between low formation probability and induction time. It's also really important that we use the gamma distribution here and the fits, because it reduces our dependence on the shortest induction times measured. So say if we measured 100 formation events, we might only have 3 or 4 formation events in this region that are actually of interest, but we need to use the full distribution, so say all 100 events, to smooth out those events at low formation probability, and it gives us higher resolution as a result of that as well. So now what we're looking at on this slide, this can get a bit confusing, so I'll try and step you through it. But we're looking at TIPT, so that induction time, changes as a function of what acceptable formation probability we can tolerate. Instead of looking at acceptable formation probability, though, we're now going to look at the probability of remaining hydrate-free. So that's just 1 minus our acceptable formation probability. And we're looking at it for 3 different margins. We have a 99.9% chance of remaining free, 99, and 90. And of course, we have our 2 inhibitors here. We've got Inhibex 501 and 713 over their full subcooling range. What we see at 99.9%, interestingly, is that Inhibex 501 significantly outperforms Inhibex 713. So it's able to delay hydrate formation to a longer period with 99.9% confidence. But when we look, that's also present for the 99% system as well. What's interesting though is when we start to look at lower formation probabilities, higher formation probabilities or lower chances of remaining hydrate-free, you start to see that the performance of these two chemicals, so the intersection of these red lines with these two data points, starts to become comparable. And what that's telling us is that essentially Inhibex 713's performance is comparable, if we can tolerate a higher formation probability. So what this is then paving the way to, I guess, it's the very, very first steps to looking at how economic cost weighs up against your risk. So if we have two different inhibitors that have vastly different costs, but they both give us a similar value of TIPT at 99%, then we can start looking at that cost-based optimization. Now, I've shown you basically time results so far. What I'm going to translate these now to essentially is now formation risk regions. So we've got a very simple example system here, which is a 100-kilometer tieback. And over this tieback, the max subcooling is about 6 Kelvin. So we have the pressure and the temperature trace here. And what this looks like in PT space is shown on this bottom diagram. So we have our pipeline PT trace, which enters the hydrostability region and has that max subcooling at around here. So what we're looking at now in terms of TIPT is the value with respect to that max subcooling. So we're doing quite a conservative estimate. The total residence time in this system is about 5 hours. And we're going to look at how the different probability margins change over the tieback length. So on the bottom one here, we have Inhibex 501, and on the top, we have Inhibex 713. So for both inhibitors, where the subcooling first becomes positive, which is where this inhibitor, the pipeline trace, just dips into the stability region, is the same. And that essentially corresponds to the chance of remaining less than 100% chance of remaining hydrate-free. So once we get a positive subcooling, we can no longer be 100% sure that we won't form hydrate. When we look at the 99.9% chance of remaining hydrate-free, we actually see we have a longer region for Inhibex 501 compared to Inhibex 713. And that's again back relating to the residence time and those TIPT values that I showed you before. And again, interestingly, if we can tolerate a 1% hydrate formation risk, we're actually getting the same space region now. So before we were looking at time, now we're looking at space. We're seeing it's about the same region that the chance of remaining hydrate-free drops below 99%. This is just a demonstration, I guess. There's no way we're suggesting that this should actually be used, but this is the power of using these sort of measurements and how we can start to look at different inhibition performance. The other point I would make here is that the reason why this is 99% before, when I told you earlier it was 90%, is that we've changed the subcooling slightly. And that really comes back to our previous discussion about how inhibitor performance is subcooling dependent. So I guess in terms of wrapping all this up and the work we've done so far, and a way that we're suggesting now would be the best way to screen KHIs, is firstly, we use constant cooling experiments to screen our whole set of KHIs. So we might have 10 options initially. And what recent work by Peter Metaxas was able to do is show that your constant cooling experiments can allow you to eliminate ridiculous options. And you can also test for interactions between, say, corrosion inhibitors and KHIs. And pretty much what we're going to get out of this first stage is our best, say, 2, 3, or 4 inhibition strategies. We can then subject these promising inhibition strategies to constant temperature testing. So that's the induction time data that I've showed you today. But it's really important that when we're evaluating this constant temperature testing, that we do so at the conditions that we think are going to happen in the pipeline. So for example, if you want to do it at a low subcooling application, even if you can't target those subcoolings due to long induction times, you need to measure the induction time over a sufficient enough subcooling range that you can extrapolate back with confidence. Finally, we need to look at, or we can look at the TIPT values for various threshold probabilities. And that brings us back to the fundamental link between inhibitor selection or inhibitor performance being a function of how, I guess, what risk or formation likelihood we can tolerate in the system. So hopefully, in terms of what I've showed you today, is that it's really essential that we need both induction time and growth rate measurements to screen sets of KHIs. If we use one of these, we might not get a full picture or understanding of what's going on. The apparatus we have here at UWA, HPS-ALTA, can provide these in a time-efficient manner, which is a barrier to traditional apparatuses conducting these sorts of tests. The KHI rankings that we get out of these results can change with subcooling, and that tells us it's really important to look at inhibitor performance at your representative system conditions. And finally, the gamma distribution can accurately describe KHI formation probability, which is really key when you want to start looking at which inhibitor is best for your system. So before I go any further, I'd like to thank Pete, Zach, Eric, Vincent, and Bruce for all their help they've given, not only with this presentation, but with the research done so far. And yeah, thank you.